So definition. An orthogonal transformation is a linear transformation that preserves the length of a vector. Okay, very important one more question. Orthogonal transformation is a linear transformation. Whether it's a linear transformation or not. Very important one more question. So x squared plus y squared, the component will be your x squared plus y squared, and you are going to add these two. This is called the length. The length preserves. Okay, the length is the same. Orthogonal matrix. Take, for example, just take a matrix A. So now we are going to convert everything vector into matrices. Okay, every vector into matrices. So we are going to consider a matrix A. N by 1 matrix, n by n matrix. And A, I, J are the elements. They belong to R. Okay, I, J, I stands for rows and J stands for columns. So A, I, J are elements in a matrix. They belong to R, real space. Now, A transpose A is nothing but I. So probably you would have studied in +2 itself, okay, or in undergraduate mathematics. A transpose A will give you I. What is A transpose? You are going to consider A matrix. You are going to change the rows into columns. Okay, that's called a transpose. Changing the rows into columns or changing the columns into rows. So that will give you A transpose. So A transpose with the matrix multiplication will give you I. Here A is orthogonal matrix. If it is so, then A inverse, which is equal to A transpose, this condition is satisfied, then A is orthogonal matrix. I repeat, suppose you are going to have A as a matrix. If this condition is satisfied, A inverse, which is equal to A transpose, then we say that A is an orthogonal matrix. See, we know that A transpose A equals I. Okay, we just multiply on both sides by A inverse. See here, A transpose A equals I. I am going to multiply on both sides by A inverse. See here, A inverse on both sides by A inverse. What is A inverse? A inverse is your I. A inverse is your I. So A inverse A is I is unitary matrix. Okay, unitary matrix. So this becomes A transpose, which is equal to I multiplied by A inverse is A inverse itself. So A transpose, which is equal to A inverse. So A inverse, which is equal to A transpose. Is it okay? We started with A transpose A, which is equal to I. We ended up with A inverse, which is equal to A transpose. That means A is an orthogonal matrix. Okay, the resulting A vector is the same length. So we will have the same length. The transformation of A preserves orthogonality. The transformation always will preserve orthogonality. Orthogonal transformations preserve orthogonality. Consider an orthogonal transformation T. So we are going to consider here as a translation. Okay. With the vectors U and W. So U and W in Rn, they are orthogonal then, and we are going to have a translation. So linear operator acts on U, which is nothing but Tu, acts on Tw, which is nothing but Tw. If the distances are preserved, then the angle, that is right angle before the transformation, must still be right angle. See, here also right angle, here also we have right angle triangle. Angle is preserved, length also is preserved. See, this is your right angle triangle. After the translation, this also will be a right angle triangle with the same length, with the same angle. So length and angle are preserved, they are the same. So before the transformation must still be right angle triangle, after the transformation due to Pythagoras theorem. So any doubt? It's very simple example. Now orthogonal transformation preserves orthogonality. Very important question. Okay. Orthogonal transformation preserves orthogonality. We are going to prove this one. Orthogonal transformation preserves orthogonality. Preserves orthogonality means length is preserved. Okay, after the linear transformation, length is preserved. That's called preserves orthogonality. Now we are going to prove that the combined system, which is equal to individual system. Now what is this one? Two lines. This is called the length. So this is called two lines inside. This is called the length. So length is preserved. We are going to check. And of course, this condition should be satisfied for linear operators. We know already. So you have combined system which is equal to individual system, addition of individual system. Now we know from linear transformation, we know about this. From the rule for linear operator, linear transformation is given by this one, we know already. T of u plus T of w, which is equal to T of u plus w. So this is for the linear operation, we know. Okay. So because of T is linear. Now this is orthogonal. As I said earlier, invariant. Can you remember the word invariant? That means T operator operates on V, will give you V. Then reverse also is possible, as I said. Correct? Can you remember? The reverse also you will get the same answer. Here we have taken the reverse one. Usually we will go from here to here, that the reverse one. So T u plus W will give you u plus W because T is orthogonal. Now u plus W can be written as length u squared plus length W squared. So u and W are orthogonal to each other. So this is nothing but this. So this is equivalent to this. So thus we have proved. So length is preserved. You have taken the length as a combined one. You have taken the length as a combined one. Now you have taken as length as individual one. So T is orthogonal. So thus the length is preserved. Okay, thus the length is preserved. So orthogonal transformation preserves orthogonality. Now we'll go for one small problem. So first you just take A matrix is given as 0, 1, minus 1, 0. Now go for A inverse. You just take A inverse. A is given as this. What is A inverse? A inverse is that you can calculate. So which is nothing but 0, minus 1, 0. You multiply with the matrix, that will give you 1, 0, 0, 1, which is nothing but your I. So A inverse is nothing but your unitary matrix. 1, 0, 0, 1. If A is orthogonal, then A is invertible or not? So answer is yes, because A inverse exists, and of course this is the condition for any orthogonal property. So A inverse, which is equal to A transpose. Suppose if A is orthogonal, then A inverse is also orthogonal. For example, just take A transpose which is equal to B. For example, just take A transpose equal to B. Just calculate B transpose. B is nothing but your A transpose. So A transpose I can write. What is B? B is nothing but again A transpose. So A transpose. B transpose is there. So A transpose with transpose. And again that will give you again A itself. So A itself. So you have A transpose. A transpose of transpose will be A itself. So A transpose of A is nothing but your I. So A transpose of A, which is equal to I, can be written as A inverse. This A and this A will get cancelled. So A transpose equal to A inverse. So A inverse equal to A transpose. So this must be A inverse must be orthogonal. We started with A. We ended with A inverse. If A is orthogonal, A inverse must be orthogonal. No other. Is it okay? Very important one more question again. If any matrix A is orthogonal, A inverse also must be orthogonal. So it's very clear. It's the proof. Now orthogonal rotation matrix. So now we are going to have a rotation. So orthogonal matrix will be applicable for rotation and inverse. So we are going to have the discussion on rotation matrix as well as inverse. So now we know that A transpose equal to I. Then we are going to consider A is a rotation matrix. We are going to consider A equals, just consider A, B, C, D. It's a matrix. Okay. So A transpose equal to I. So we can write this as A transpose is change the rows into column into rows. So A, B, C, D becomes A, C, B, D. Correct. You are going to change A, C as A, C here. Then B, D as B, D. You have changed the rows into columns. Any doubt? Which is equal to, we are going to prove that this is 1, 0, 0, 1. Because already we know that A transpose equal to 1, we know already, I, we know already. This is 1, 0, 0, 1. So you multiply these two. Ordinary matrix multiplication, 2 by 2 matrix. You multiply these two. So that will give you A square plus B square. Then second one will be AC plus BD. Then this one will be not C square. This will be AC plus BD. Then the last one will be C square plus D square. Any doubt? Now we are going to equate these two. So this component should be equal to this one should be equal to this, and this must be equal to this, and the last one should be equal to this. So you have now A squared plus B squared equals 1. Okay, it's very simple. So you just go for B squared, which is equal to 1 minus A squared. Similarly, C squared plus D squared equal to 1. So that will give me, just take C squared as 1 minus D squared, just for the time being. Then the remaining one, AC plus BD equals 0. Similarly, AC plus BD equals 0. Suppose AC plus BD equals 0. So it means AC equals minus BD. You just square it. So you have A square, C squared equals B square, D squared. You substitute for C squared. Very good. So you have A squared. Instead of C squared, substitute for 1 minus D squared, which is equal to B squared. Substitute for B squared, which is nothing but 1 minus A squared. So D squared, you just keep it as it is. We multiply now and simplify. So you have A squared minus A squared D squared, which is equal to D squared minus A squared D squared. This will get cancelled. You bring this term to that side or bring this term to this side, both will get cancelled. You have A squared equals D squared. We just keep this result as A equals plus or minus D for the time being. Any doubt on the slide? Our aim is to prove rotational matrix, orthogonal rotational matrix, whether the length is preserved or not. We are going to check. Okay. Any doubt? A equals plus or minus D. Now we'll go for the case 1. If A equals 0, we got the result as A equals plus or minus D for the matrix A, B, C, D. So if A equals 0, D equals 0. Correct? So if A equals 0, so D will be equal to 0. You substitute A equals 0 in the second one. Yes, second one. B squared equals, substitute A equals 0. This case, B squared equals 1. So B equals plus or minus 1. Is it okay? Simple one. What of C? C squared equals 1 minus D squared. D also is equal to 0. So this will be C equals plus or minus 1. So you will have 0 plus or minus 1 plus or minus 1 0. So this is one result. Suppose if A is not equal to 0. If A is not equal to 0, then we have this is not equal to 0. But A equals plus or minus D. So both are equal. If both are equal, B squared must be equal to C squared. I repeat, see, A is not equal to 0. Correct? So if A is not equal to 0, here A and D are equivalent. A equals plus or minus D, equivalent. So these two terms are equivalent on right hand side. So left hand side must be equal. So which is nothing but B squared equals C squared. So B equals plus or minus C. Okay. Or else I can write B equal to plus or minus C as C equals minus or plus B. Can I write? See, B equals plus or minus C. I can write C as minus or plus B. Now the matrix A, B, C, D can be written as, you can write either substitute for minus sign, then plus sign for C. Like A, you have A, B. Instead of C, you can substitute minus B. Instead of C, you can substitute plus B. Okay. And of course, A equals for one side will be your D will be your A and D will be your minus A. So that's why we written two matrices, either this side or that matrix. Now, what is this one? This is nothing but your A squared, just like the determinant. You have A squared plus B squared, which is equal to 1. Take the determinant, which is nothing but A squared plus B squared equals 1. Here also we have A squared plus B squared equals 1. So what does it mean? A squared plus B squared equals 1. This is nothing but X squared plus Y squared equal to 1. Equation of the circle. So this is a rotation matrix. We started with matrix A. We operated, A is a rotation matrix. We operated with A dagger, which is equal to 1. And at the end, ultimately we have obtained A squared plus B squared equals 1, which is your equation of circle. So x square plus y squared equals 1. A, B lie on the circle. Similarly, C, D also will lie on the circle. So any 2 by 2 orthogonal matrix, either rotational or reflection. Reflection also will work out. Reflection matrix. Here theta is the anti-clockwise direction or clockwise direction, and xy is given as r cos theta, r sin theta. In terms of polar coordinates, we have written as. So this is your x and this is your y. For the time being, just take r equals 1. So xy becomes exactly like this. So we can write this in a matrix as cos theta, sin theta, minus sin theta, cos theta, which is nothing but rotational matrix is orthogonal because the vectors are orthogonal. The determinant equal to 1. Similarly, you can go for the reflection matrix also. For the reflection matrix, similarly you can try. So this becomes cos theta, sin theta minus cos theta. Here the determinant is minus 1. When you are going to have a reflection, exactly this will be in the opposite direction. So that's why it termed as minus 1. For rotation, the length is same. Okay, for the rotation, the length is preserved. When you are going for the reflection, this will be exactly in the opposite direction. So that's why determinant is minus 1. So which of the following matrices are orthogonal? We will find out. Just don't look at the answer, you just try. And we have two matrices written on the slide. You just check whether which one is orthogonal or not. See, minus 8, 6, 6, 8. So this is matrix, okay, matrix A. Now I am going to interchange rows into column, column into rows. Okay, 1. Then second one is minus sign exists. So this must be orthogonal matrix. This must be orthogonal matrix. Orthogonal because one is perpendicular to another one. One is perpendicular to another one, orthogonal matrix. So this must be orthogonal. Column vectors are unit vectors and they are perpendicular to each other. They are perpendicular to each other. We are going to change rows into column also with minus sign exists. So this must be perpendicular to each other. What of this matrix? Try this matrix. 2, 6, 3. 2, 6, minus 3. Okay. What of 6 minus 3, 2? The next one. What of next one? 3, 2, 6. 1 minus sign. Of course, 2 will work out. The other one, minus sign doesn't exist for all the components. See, minus sign doesn't exist here. So that's why this is not orthogonal. The first and third column vectors fail to be perpendicular to each other. First and third column, they are perpendicular. They are not perpendicular to each other. So this is not orthogonal to each other. Okay. So we started with direct sum of invariant subspaces. Okay. So that is different from ordinary sum, and ordinary sum is just addition. And in terms of vectors, linear vector space, we can say that even though it works out for two properties, one is vector addition, another one is scalar multiplication. If it should obey with the overlapping term 0, what we call this as direct sum. So three conditions should be satisfied. One is the overlapping term, very important, overlapping term. That the intersection of two subspaces should be 0 element. This is overlapping term. Then second one is vector addition and third one is scalar multiplication. Then we say that those two subspaces they come under direct sum. Okay, then the last one we checked a bit, orthogonal matrices. If A is an orthogonal matrix, A inverse also is orthogonal matrix. So A transpose will give you always 1. And we have given one, we have shown one example too. One is rotational matrix, then another one is reflection matrix. So that's the end. We will see in the next class. Thank you so much. Bye.